how much of this frequency we have in this signal. And A2 basically tells us how much of 2F we have in this signal. A3, A2 and B2. So A3 and B3 tells us how much of 3 times the fundamental frequency we have in this signal. Right, so that basically helps us in designing filters if we wanna, if just to figure out what are the dominant harmonics or dominant frequencies in this signal, so that we can filter them out. If this is unwanted, let's say like we wanna filter this signal so that we come up with something that looks like this, right? Looks like the fundamental frequency. So we need to filter out each of them. So first of all, we have to figure out which one of these components are dominant, right? Do we have, like, for example, a second harmonic or third order harmonic or fourth order harmonic, fifth order harmonic, and so on? Then we can design a filter for that specific frequency. So it's a very useful tool, and so we're gonna use this to analyze the half wave inverter and a full wave inverter. So let's also see what the original formula for Fourier transform is. So the original formula for Fourier transform is this. It basically tells us that this signal can be written as a DC value, right, which is gonna give us the same as the average of the signal over the period. So this is the same as F0 plus the summation of cosines of 2 pi over Tn times T plus Bn times sine of 2 pi over Tn T, where n goes from 1 basically to infinity. If you want to be accurate, like, it has to go to infinity. But like in practice, if you find out that a n's and b n's are getting smaller and smaller, we limit the summation. So for example, if a n becomes 0.00001, then we can ignore the higher order harmonics. But this is the original formula for Fourier transform. Okay, and for the formulas for ANs and BNs are basically given as such. AN is 2 over T integral over the period, so it can be from 0 to T or from any time from A to A plus T. We usually go from 0 to T of f of t cosine of 2 pi T times nt dt. And for Bn is basically 2 over T, the same thing, but instead of cosine we have sine. F of t sine of 2 pi over T times nt dt. Okay, so this is what Fourier transform is. I don't expect you to memorize the formulas, but I want you to understand what Fourier transform is for. Like, what is it good for? So so now I'm gonna use Fourier transform to analyze the half wave inverter first and then full wave inverter. Also full wave inverter or half wave inverter, they're also called half bridge or full bridge inverter. Yeah, so it's okay. I can erase this one. Okay, so first, let's start with the half wave or half bridge inverter. So in the previous video, I showed you that the signal that we get out of the half wave inverter looks like this. VDC over 2 and negative VDC over 2. It only has two voltage levels, VDC over 2 and negative VDC over 2, and it's periodic. Okay? So first of all, let's find the, so this is output voltage. First of all, let's find the DC value of this signal, which is also like the zero frequency component. Let me just call it V, VDC or V0. Okay, you already know this. The DC value of a signal is the 1 over T integral from 0 to T, basically over the period of the signal, Vt dt. Okay, we also can use the formula from Fourier Transform. A0, according to the formula, it's 2 over T integral of 0 over T V of T cosine of 0. Let me just call it cosine of 2 pi over T times n, which is 0, times T dt. Cosine of 0 is 1, so it's gonna be A0 becomes 2 over T times T, 2 over T times integral of 0 over T Vt dt, whatever it is. Okay, that's why, like, when I wrote the Fourier transform, we had A0 divided by 2, because this 2 has to be cancelled out with this one, and this is going to give us the DC value of the signal. Now, for half wave or half bridge rectifier, this integral, it's very easy to calculate, because the integral